In this video, we're going to learn about strengthening method. Strengthening is done in the material in order to improve the mechanical properties of material. Now you may have a question in your mind. What's the need for doing strengthening? Because instead of doing strengthening, in the alias itself, we can select the good quality material, right? Why we are not doing? Take this point. In manufacturing, some object demand higher hardness in the application. But to manufacture it, the machinability comes from lower hardness. See, there is a contradictory idea, am I right? Yes. So in such a scenario, what they do is, first initially they will start manufacturing with a low hardness material and then they satisfy the application need by strengthening methods. Strain hardening. This is one of the strengthening method, and here I have taken the stress strain diagram. Okay, so actually this is a familiar thing to you. Just like tensile test, here I going to conduct the experiment. Okay, so we are well familiar when the pull is given to the material. What happens initially, for some extent of stress and strain, it will be showing the elastic deformation, isn't it? Yes. So that means it will be linear. It will be linear in the curve. I can say it will be linear for some extent, and then what happens? It will be a plastic deformation in nature, and what happens? It will be tracing the curve as this manner. Okay, and I'm not going to the entire things, because here I have stopped the experiment before the fracture occurs. So I have stopped with this. So initially it's a elastic deformation, and next is it is plastically deformed, and here I can note the point. That means this is the point I can say yield stress. Okay, this is the point I can say yield stress, and this is the yield stress. Yield stress in the sense, we know the point at which the plastic deformation begin and the point where the elastic deformation ends. That's a right thing when we say about the yield stress. So this is a point. Okay, and for your remembrance, I can say I can show the diagram for the work. First, just it will be rectangular bar. Okay, so for this only we have conducted the tensile test. Okay, so what happens? This is the exact thing in the initial. When the tensile load is applied, obviously we are well familiar in that it get elongated, and it comes like this. When we compare with this, when the plastic deformation is experienced in the material, there will be reduction in the area, something like that. You will look the things. Okay, so this is the plastic deformation. Now the material is deformed plastically. So now here what I going to do is, with the plastic deformation, I going to stop the experiment. Okay, I going to stop the experiment. I going to unload the load here. I going to release the load. So what happens? It will traces the path. If you capture in the stress strain diagram, it will capture the path as this manner when unloading. Okay, so and I can say from this stress strain diagram, it is evidently seen it is capturing with the energy del strain. Okay, so I can say this is a plastic strain energy. So it is capturing with the plastic strain energy when the material is unloaded. Okay, so now I going to do one thing. Just with the same deformed material, after unloading it, I going to retest it again. Okay, so I'm going to retest it again. So what happens here? We can see when it is unloaded, we can see the interesting fact, and as well it is experimentally proved that the yield stress. So initially plastically deformation, elastic deformation will be there, right? So here you can see the yield stress is increasing to the level, that means where the what plastic deformation stop. Okay, so where we have stopped the unloading, up to that particular point it increases the yield stress. So here is the yield point when we are conducting the retest. Here is the yield stress. So I can say this is initial one, so I named as sigma y naught, and here I going to quite differentiate with sigma yi. Okay, so this yield stress which is obtaining when the retest is done. Okay, so while retesting, it is taking the linear path during the plastic deformation in the retest. But the interesting fact is here that yield shear stress is increased than the previous one. Okay, and it follows the curve with the plastic deformation. From this curve, it is evidently seen that yield stress sigma yi is greater than sigma y naught. That means the retest obtains higher yield stress than the previous one. So from this we can conclude that the deformed material has higher strength. That means the deformed material has higher strength. So now I can describe the strain hardening as it's a phenomena. That means ductile material becomes harder and stronger as it is plastically deformed. See, we have general idea about deformation. That means whenever any material experiences plastic deformations or elastic deformation, definitely there will be a dislocation in the atomic level. So that's why I have written here plastic deformation increases the dislocation density, and we also agree dislocation weakens the crystal. Definitely if any dislocation happens in the material, it's gonna weaken the crystal. Am I right? Yes. So from this two idea we shall come to the conclusion that deformed crystal should be weaker. So we can come to the conclusion deformed crystal should be weaker. Do you agree with this? Yes. But I can say this idea is wrong, because from this stress strain diagram we understood that means when the plastically deformed material is reloaded again and deformed, we have came to the conclusion that deformed crystal is stronger. That means deformed crystal is stronger. Deformed crystal is stronger. And why it is happening? That we're going to see here. I can say the reason is because of dislocation interaction. Now just think about the deformation in material. Just I can say when the plastic deformation start generating more and more dislocation, what happens? Each dislocation will interfere with each other, and as a result what happens, the motion of the dislocation will be stopped. So that's the reason the strengthening is happening. So here I can put the important point. When plastic deformation starts, what happens? The dislocation repulsion will be there. And so because of the repulsion, when each dislocation interfere with each other, there will be a repulsion, and as a result, what is happening? Motion of dislocation is being stopped. Therefore I can say strengthening will occur. Strengthening occurs. Next one is refinement of grain size. This is one of the another strengthening method, and in order to understand this refinement of grain size, I have shown you two crystals. One is a single crystal and next one is a polycrystal. Okay, now just focus on this single crystal. Now if I want to say about the single crystal, I can say the unit cell in this crystal will be oriented in the same way. That means will be in the regular arrangement. Okay, regular pattern it will be arranged. I can say this polycrystal will be lying on the other hand, and I can say the orientation of the unit cell will be goes on changing from region to region. Okay, it will be goes on changing from region to region. If I consider in this region, this is the pattern of the arrangements of a unit cell. In the next region, you can observe the different manner of the orientation. It goes on changing its orientation. It will be like this manner. Because of this change in orientation, you can see the formation of the grain boundaries between the unit cell. Okay, you can see formation of grain boundaries. Okay, I can say these are the grains, these are the grains, and these are the grain boundaries. Okay, so now I just want you to remember the slip. So we are well familiar in slip. In the last video we had a great session. So I think you are familiar in the slip, for which I have taken the bar, this bar. In this bar the slip going to happen. Slip always happens along the slip line. Okay, so this is slip lines going to happen, this slip, right? So it's the initial position. When the slip happens, what happens? One part of crystal will be gliding along the slip line, something like this. Am I right? It goes on gliding, so that you can see dislocation. You can see the dislocation in the materials. Dislocation motion here, it happens in this direction. Okay, so this is the slip. So now I just going to consider the slip going to happen in this single crystal. Okay, so in this single crystal I going to consider this is the plane. We going to consider the slip, right? So if it is a slip plane, what happens? This slip tends to form the dislocation, and what happens? This dislocation will be moving all around the throughout this single crystal. Okay, if it is happens in the single crystal, it just affect entire crystal completely. So but what I come to say here is, if you consider the polycrystal, I can say if there is a dislocation in one grain, if there is a dislocation in one grain, this grain boundary in the crystal will be acting as a obstacle. What grain boundaries? Grain boundaries will be obstacles, will be acting as obstacles. Because of these obstacles, the dislocation in the polycrystal will be slowed down from the region to region. It just don't happens like a single crystal. That means it won't affect the entire material. So when comparing the coarse grain and fine grain, you can see evidently the grains and grain boundaries in the fine grains is much more than the coarse grain. Am I right? So I can say the obstacles for the dislocation is higher in the fine grains. So from this I can conclude the strength of the fine grain is much greater than the strength of the coarse grain. Okay, so therefore in the material science, in order to increase or in order to strengthen the materials, what they do is they used to reduce the size of the grains. The process of reducing the size of the grains inside the material is known as refinement of grain size.